Yeah, so today we have to see one like Python example for polynomial regression, like how can you make a curve, I mean a fitting of curve in the data set on the data set, and that's polynomial regression. And also we will see the concept of bias versus variance, that when we say, like last time we have seen this, that you can have two possibilities and we have to find a model which is between these two possibilities. So one point can be like you have a data point like this and you are fitting a line over it. Now this data point
Mhm.
is actually a curvy in nature, right? The trend shows that it is curvy in nature. So but you are fitting a line over it. So there are two things happening. One, the cost function of training data itself is high. The model is
Yeah.
underfitting. This kind of model is called as underfitting. Uh, Underfitting, or it is also called as high bias problem. What I actually literally mean by bias is the difference between the model which is fitted and the training data itself is very high. And as the training data error is high, you also expect that the test data, when the test data will come, which will be of the same pattern, that test data will also have a high large difference from the model fitted. So here the training data as well as the test data, both the data are high only. Okay, then we also talked about some another scenario when on the same data, on the same kind of data, you are like you are not fitting a line. Line is basically degree 1, but you are fitting a very high degree polynomial, say degree equal to 10. So in this case, your line will be, passing through each point, trying to cover each point and passing lot of
Mhm.
having lots of curve. So this is like d equal to 10. Now both these cases are bad. Why is this bad? Because here the training data, the characteristic is the on training error will be almost equal to 0, because it passes
Yes.
all the training point very nicely. But once on this particular data only, on these patterns only, once you will get the test data, you will find that on the test data it performs very poorly because of high fluctuation in the model. In the model itself, there is a huge fluctuation, and because of that, the cost function on the test data, I mean, will be high. So these are the two differences. Here, this model is called as overfitting. Also, this is known as high variance. So the difference between both are not commended. Both these models are wrong. Why? But why? You must know the difference. You must understand the difference. That in the high bias or underfitting curve, the model which is fitted itself is poor. So even on the training data also it performs bad, and on the test data of course it is going to perform bad. But in the
Mm.
overfitting case, you have learned it so well that each and every training point it is unnecessarily, passing through exactly it, and the error is 0. But due to the high degree, or you can say the model is so has learned so well that when on the test data, which is on the same pattern, um, the error will be high because of the huge fluctuation in the line. So what was actually needed was, like, on some model on the same data set, if you say some model which should be of some say degree 3 or degree 2, which can actually grab the pattern of the data, or capture the trend of the data, so that in future if any data comes it can predict it well. So this was the typical example we have seen. Just to revise you, I have told you again this thing. Now, in here, if you see what can be done. So basically, in variance problem, what you can do, degree uh, you decrease. In this case, degree you can increase. Other than that, what you can do in a high variance problem, you can increase the training data. So if you are increasing the training data, there are lots of data from the training historical data. Then in order to fit all the data, this curve will be little smooth. So because when your degree is high, it tries to fit all the training data. Now when you have lots of training data, it cannot fit everyone with a huge variance. So the variance will automatically reduce. So that's one thing, that as you increase the training data, your error will be reduced in this particular case. In this case, your model itself is so poor that even on you go on increasing the training data, this line will be performing bad. Okay. So this particular problem we are now going to see with a Python example. Okay. Now, as in this bias and versus, variance problem, we have seen that this it's not only line which we are fitting, which is degree 1. We will be also fitting a, let's say, line of a model of degree 10. So then that degree 10 will be a curve fit, right? So this curve fitting is also known as polynomial regression. Okay, it is also known as polynomial regression. So
Polynomial.
in the same example, we will be seeing both the things, polynomial regression also and bias versus variance also. So we will be using polynomial feature, which can make the equation of line something like this. Theta 2 x1 square, theta 3
Square.
x1 cube.
X1
Yeah.
cube.
So I told you there were two things. One is single variable is very nice. Single variable is very simple. That is simply theta naught plus theta 1x. Now there was another thing which is called as uh, regression with multiple variable, where you have other features also, x2, or say dot dot dot, say theta 4 x4, like this. So this is one thing, this is another thing. Now polynomial regression is something different, which says you will have maybe x1, then with theta 2 you will have x1 square, maybe theta 3 you can have x2 but x1
Cube.
square. Anything can happen, any terms you can use. So these are the other
Yes.
features. Now just one more theoretical part which is very important to understand. We talked about bias, high bias, and we talked about high variance. Now, how do we decide that which model to choose? Suppose I started from degree 1 and I went to degree 2. I mean degree 10. Now, on degree 1 I am getting a high bias problem. On degree 10 I am getting a high variance problem. So how do we
Yes.
choose which is my best model? I know that in between with some degree 3 or degree 4 it will be best. But how do we choose that? So a typical, approach which is taken to choose the best model is from your historical data. Suppose you have 30 observation in the historical data. Okay. Suppose you have 30 observations, or I say data points,
Okay.
or I can say X 30. So what I will do, I will keep I will keep 10 data points in reserve. I will only train my model. I will only train model on 20 data points. On 20 data points. This is the first thing I'm going to
Any
do. Yeah.
any 20 data points?
Any tender. Randomly you pick 20 data points that you will use for training the model. Now in loop from degree 1 to 10. In loop, what I will be doing, I will train the model. So model.fit, and I will pass this degree here equal to d. So in each first time I will fit it with 1, then 2, then 3, huh? And then from this particular model I will predict it. I will predict these 10 data points which were left out. This 10 data point which I have separated out from the previous observations is called as validation set. is called validation set. So
Validation.
yeah, so there is a training set on which you train your model. There is a validation set on which you validate your model, and then there is finally test set which on which you finally claims your accuracy. So there are three kinds of data, which in regression you always divide your previously historical data into three parts: training, validation, and test. On test, you will claim your accuracy, which we have seen last time in the program. That if you have
Yes.
plus minus 2 lakh, how much data points are you predicting correctly? So that is test set. That is kept different. Now in this 30, I have kept 20 for training and 10 for validation. Now why is this 10 validation data set used? That actually I wanted to tell you. So why this 10 validation data set is used is, this 10 validation data is also unseen data, completely new data, isn't it? These 10 data points are not used while training the model, while fitting the model, while knowing the theta naught, theta 1, theta 2, theta 3, whatever parameters are there, while performing the gradient descent and all those mathematics. We never include these 10 data set which are in validation set. Okay. But
Okay.
why we are using this validation data set is, we will start with degree 1 and then we will predict it with these 10 data points. Okay, and we will calculate the error. We will calculate the error, that error calculation also we have seen in the previous example, like how you can calculate the error, right? The actual minus
Yes.
predicted square, and
Predicted
you,
square
you do np dot
1 by
sum
n.
and then you divide it by 96 or whatever, right? So this we
Yes.
have seen. So I will calculate the error with degree equal to 1. Then that particular thing I will perform the same thing with degree 1, degree 2, degree 3, dot dot dot, degree 10. For all these degrees in loop, I will test my I will calculate my validation error. This cost function
Okay.
I will calculate. So what you will find an amazing thing. What you will find is, see, suppose this is my validation error. Okay, on x-axis is my
Okay.
validation error, and on the y-axis, sorry, I made it wrong. On y-axis will be my validation error, and on
Okay.
x-axis it will be degree.
Okay.
I,
One,
I-
two, three, four.
yes, yes, yes. I am going in loop, right? So in loop, I will be having degree. So from 1 to 10. Now what
10.
what you will find is, as you are increasing your degree, so initially what will happen, on when degree is equal to 1, my validation error will be high on the 10 data points which are not used in training. On this I am calculating my validation error. Okay, so basically if you want to see this, I can visualize it like this. Suppose your data points, training data points were like this, right? And now you fitted a
Yes.
line with degree 1, you fitted a line. So on the validation set, the 10 points which were in the same pattern, but you have not included in the training, right? On
Yes.
these the error will be very high, isn't it?
Yes.
So this error will be high, but as you move toward degree 2 or degree 3 or degree 4, the validation error will go down. It will go down, go down, go down, go down, go down. Huh? Why? Because when you are, see, in here in the same example, when you go for degree 2, it will be something like this. Then degree 3, it will
Hmm.
be something like this. Degree 4, it will be something like this, right? So you
Yes.
will find that on the training data, you will find that on training data, your degree is going down, going down, going down, and as you are moving towards degree 10, it will be almost zero.
Okay.
The training error I am talking about. Because whatever training error you had, like this was your training data, isn't it? Now
Yes.
with degree 10, it will fit them exactly, right? Like this.
Yes.
So the error will go down. Now on validation data set, the DP, here I am also considering training data set and validation data set. Now on this particular 10 data points which were not included in training, like here, 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 what you will find that initially when it was a line, the error will be high. Okay, the error will be high. It will
Hi.
it will go down with the as you will increase the degree, like this degree or this degree, so it will go high. But after some point, like maybe degree 5, you will see again your validation error is increasing. Why? Because on the validation error, when you will be having a degree 10 curve, the validation error is new, right? It was not included in training data. So when it was not included in training data, these 10 points, it has not overfitted it, it has not gone through it. But due to the fluctuation in the model, on the validation date, your error will be huge.
Mm,
You got my point? So
okay.
if you have a training data like this, suppose your at degree 10 your model will be passing through all these training data, but validation said the error will be high. So after this cutoff, it goes on increasing, and this cutoff, this trade-off basically, this particular degree, basically suppose it is 5, I will take this model as the best model, best suited model for my data points, for my application. So this is the degree finally which I am going to choose, because I am seeing that before this degree, this region is a high bias region. It's a high bias region because model is underfitting. This is basically underfitting. The cost function is more here, although it is reducing, but it is more till in this region. Now in this region, this model was leased. Okay, in this region, the model was leased, and now if you see in this region again the model has increased. I mean again the error has increased because of the fluctuations, okay.
Yes, yes.
So this region is called high variance region. So this is very important concept, and this particular graph I am telling you, this graph is, I mean, the most topped graph when you talk about bias versus curve, variance curve. This graph is
Mm,
hugely talked in the interviews, or maybe in the general discussion also. If somebody is asking you for a demo of linear regression, or you are maybe say presenting linear regression to somebody, if the guy knows linear regression beforehand, he will finally jump into this particular graph. He will try to jump into this, because I mean I have faced lot of discussions and in this linear regression, and they will always come to this popular problem, bias versus variance. So basically this particular degree you have to choose. Okay,
mm,
because as I told you, I mean, number of times we have revised this now. That one case is when you have this kind of trend and you are fitting a line. So line itself is of less degree, and in the training data itself the error is high. In the validation also it is high. So in this region you will find that your training curve and validation curve both are high. And in this particular region of high variance, you will find that when you have actually, had a very high variance curve, a high degree curve, then your training error will be very low. You see this point? It will be almost
yes, yes.
zero because it is fitting the training data exactly. But on the 10 data points which were new, on
Mm,
that particular thing, your validation error will go high. So here it is a difference in the high variance side. The training error is very low, but validation set error is high. In this particular curve, they both go parallelly. The training data is also high. The validation data is also high, because your model is still I mean your model itself is underfit. Okay.
But why there is a huge difference between those two lines in high variance?
Yeah, I will tell you. See, this was your basically training data.
Yes.
This is the line which I am making fitting. I mean, when you fit a line,
Degree one.
you will fit line like this. So,
Mm-hmm.
and suppose these are the validation data set. Validation data
Yes.
set also come from the same pattern, right? You agree with that or not?
Yes.
So they
Yes. Yes.
now in this particular example, what do you say? Your training data, your training error will be high or low? Your training error.
Training error will be high.
And what about validation error?
Validation error is also high.
Also high. So if this is the curve which I am making and this is the degree,
Mm-hmm.
you're basically what you are saying, and here I am plotting the cost. Okay.
Mm-hmm.
So you are saying that
Yes.
at degree one both the things are high. Validation and training both are high, isn't it?
Yes. Yes.
So here both are high. Just see what I am going to make. Okay, both are high.
Mm.
When I will make degree
Yes.
2, suppose it is going to be a best fit on degree 4. Okay, so on degree 2 again the training data will be high, the training error.
Mm,
Suppose
maybe
degree,
lower than first.
yeah, first lower. Suppose degree 2 is something like this. So
Yes.
again it both will decrease little bit, right?
Yes.
So now just I am expanding, I am moving forward. So with I as I increase the degree, both will decrease.
Yes. Yes.
Ah. Now I have reached to an optimal degree, say degree 5.
Mm.
Now what will happen on this degree? Degree 5.
All
Degree
point.
5,
All points.
degree 5 will be something like this.
Yeah.
Hmm. So basically both are at the best level. I mean both have decreased. Okay, to the
Yes.
best level. Now I am again. Now what I am doing, see, now I am again going for even higher degree, say 7, 8. So what will happen? These
It's
crosses
again
are
still
these
match.
crosses are validation error. Okay, these crosses are validation
Mm.
data. So this is not included in
Okay.
training. So when you go on higher degree, it will fit your training data very well.
Exactly. Yeah.
Huh. It is
Yes.
not considering the validation data. So don't think that it will also fit the validation data because validation data is not included in training. So it will fit
Okay.
something like this, isn't it?
Okay. Okay.
Yeah. So it will go on fitting in something like this. Now, in
Okay.
this case, when it is fitting the training data very well, this particular thing will still go on decreasing as to 0
Zero.
because
Yes.
it has fitted the, but because of the fluctuation, the validation error will increase.
Okay.
Okay. The
Because of
validation error,
fluctuation.
yeah, because of the fluctuation, the validation error will increase. So this particular thing will again increase. So
But this will increase gradually. It's not increase suddenly. Is it
yeah.
right
So
or wrong?
yeah. No, it is right. It is right. So when you are basically when you have this training data and you have these validation data is the data which is not included in that while training, while fitting. So so when you have say degree 4, then I told you this is the best thing. Huh?
Mm.
When it is degree 5,
Yes.
it will be little fluctuation. Huh? So your validation data will increase little bit. But
Yes.
then you will see that with degree 7, it will be a more fluctuation.
Yes.
So it will still increase. Huh? But then you see with degree 10, it will be huge fluctuation but fitting the training data very well. So the fluctuations will be huge, right? So
Okay,
then
but I have one doubt.
yeah. Then the validation
Sorry.
data error and the training error has a huge gap. Yeah, you say.
Okay. But how we can predict like our training data and validation data? There is we can't predict like for a higher degree there is a huge gap in between because
Fluctuations.
high degree it can be lower the validation error also. It
No,
might
see,
possibility.
no, it's not possible. It's not possible because I will tell you the reason. The validation set is basically a historical data only. So if your
Yes, yes.
data points has the linear dependence, if your
Hmm.
validation data,
Hmm.
if your validation data has the linear, your whole data points, if your historical data has a dependency like this, in
Hmm.
the validation data will also lie between these only, right?
Same. Yes, yes.
Now when you are, but these are not included in training. So when you will fit a
Yes, of
higher
course.
degree,
Hmm.
it is like this. It is fitting the training data very well,
Hmm.
but it is not. I mean, you are not sure whether it is fitting the validation data also. See, it might be possible that two or three validation set. See, validation data was here, or maybe validation data was here. So then it might be
Hmm.
possible that
Yes,
it will fit say 10% of the validation set very well.
yes, yes.
When you calculate the see, when you calculate the error, validation error, you sum for all. No? You will sum it for all the 10
Yes,
validation data set.
yes.
So when you sum it, the sum total error will increase because of
Okay,
the
okay.
fluctuation in the degree. You can say, you of course you can say that no, but how can you say that on the validation data it is not going to fit? Because it may happen that on the higher degree also the validation data is fitted. So that's
Yes,
true. That's
there
true.
might be chance.
Yeah,
Yes.
but there might be chance. That is true. I
Hmm.
agree that there might be chance. But if you sum total over all the data points of validation set, the error will increase only because some point it will
Oh,
fit well maybe, but for some point due to the variation the distance will be the error margin will be high.
hmm.
Okay, so in those cases,
Okay.
the whole error will be slowly, gradually, it will increase like a ball shape. Like that's why validation error is always like a ball shape, but training error is
Hmm.
like it goes down linearly,
Okay.
or you can say
Okay.
like
Okay.
exponentially. Okay,
Okay. Got it.
yeah. So because we are always interested in some total error,
Some. Yes. Some.
some
Yeah.
total error. Okay. So
Hmm.
that's fine. Now I will
Hmm.
come to this Python example. This is a very
Okay.
good. I mean, it will showcase what I am telling. I mean, maybe this code seems long, but maybe you can make this code little modular. I have made it serial only, and then I didn't. I mean, made it modular, so that's why maybe this code seems long. But yeah, this will depict you the how 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 high bias problem is there, and you know high variance problem is there, and of course in between also when we are fitting a higher degree, you will also see how polynomial regression you can do. Okay,
Okay.
now
Okay.
yeah, so you are ready to understand the Python code? I mean,
Yeah. Yeah. We can
yeah,
proceed now.
yeah, yeah. So try to understand this code so that okay, what I will initially do, I will just quickly run this program so that
Okay.
I can show you what it is happening here. Then we can discuss about the code. Code is not anyway problem. So yeah, this particular thing. Okay, so it is running. Maybe it will take some time to read the data. Okay, so this is basically this particular example you see. The red crosses you are seeing. This the I will tell you the objective first. The objective is
Okay.
change in water level. This is a single variable problem only. Uh, Change
Okay.
in water level. So there is a dam. So we have to predict how much water will flow out of the dam due to the change in water level of the dam, maybe. Okay. I mean, so
Okay.
if there is a change in water level with some amount, how much water will flow out? That is a thing which you have to predict. Okay. So that is basically your
Okay.
X and Y. Now let us see this data point first. These are your data point, training data point basically. So how many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yeah, these 12 data points I have taken for training. Good enough? Now
Okay.
I am fitting a linear regression, curve, which is basically nothing but a degree one curve, degree one line. I mean, degree one is of course a line. So degree one I am fitting. Okay. So when you fit a degree one line, it will go like this. Now you say on the training data, how is it this model looks like? How this model is performing? How will this perform?
Can you sorry? Can you explain me change in the water level? You have taken negative to positive values.
Okay, okay. This negative to positive values is because of there are two things. There can be two things. One is when we are talking about the change in water level, of course it can increase or it can decrease, but of course when it will decrease, the water will not flow out, right? But mostly you will find this kind of positive and negative because of the concept which we have studied in yesterday's session, I mean the previous session, that is normalization. So when you
Okay.
do the mean variance normalization, I told you that you subtract your values from the mean. You
Okay.
for a data you calculate the mean and then you subtract it. So when you subtract them, some data point will go which are higher than the mean, they will be positive, and some data point which are lower than the mean, they will be negative. Okay. So,
Okay.
so that can be one of the case. The other case can be, it's fine. I mean, maybe the water level is decreasing or say increasing. In those cases also you can find that there are negative and positives. Example. Okay. So this is the data points which they have taken, just the 12 data point. So basically they had historical data around, I think 32 point or 31 points were there. Okay. So no, yeah, something like that. So 12 points they have taken for training and around 20 points they have kept it for validation. That points will come, but as of now you see only these 12 training points. Okay. Now, uh, this line, what do you think? It is a high bias or a high variance problem? So, so
It is
yeah,
can't can't say means
okay,
no idea.
no idea. Okay, so I will again maybe revise this thing. We
Okay.
say high bias. We say high bias.
Hmm.
We say it a high bias when on the training data set itself you find lot of error, when your error on the training data
It's
set is high,
okay.
and of course on the validation data set also it will be high, but we are not talking
Hmm.
about the validation error. So in high bias problem we have seen that on the training data set itself the error is very high, while
Yes.
if in the same example you see on a high variance example,
Hmm.
on the training data set it will be perfectly fit. So the training data set, the error will be almost zero. Okay, this thing we have seen, right?
Yes.
Now
Yes.
on the training data set, what do you feel like, the error is high or less?
It's high biased.
Yeah, it's a basically high bias problem
Yes.
because on the training data itself it is not able to fit. If you are not able
Yes.
to remember high bias and high variance, just remember underfit and overfit. That even
Okay.
also that seems more convenient to remember. When I say overfitting, overfitting itself means,
Difference.
yeah, suppose this is your data. Overfitting itself means that you are fitting everything with a huge curve, you know.
Okay. Okay. Okay.
And underfitting means you are underfitted, so you are not able to even capture anything. Okay.
Hmm.
And underfitting is
Okay.
called high bias, and this thing is called high variance. Good enough?
Okay.
So
Good
this
enough.
is a high bias problem where it is not able to fit the training data itself. Okay.
Yes.
Now this I have cut that particular diagram. So now this has come. So now this is
Okay.
just the on the same example of degree 1, it is showing you the error. See what is this here? Error, the cost function, the
Error.
sum total error. Okay, sum total error.
Okay.
And what we are seeing here is, see, this was your training data, this blue line.
Okay.
So your training data, when we have taken the 12 points, here it is number of training examples. Okay.
Okay.
So when we are taking the 12 data points, as we have seen in the previous diagram, there were 12 training points. So when we are taking the 12 data points, the error you see it is high enough, right? It is 50.
Hmm.
The
Yes.
error is around 50, isn't it? So
Yes.
in
Yes.
the training data itself, your error is 50. And then I told you that 12 data points they have taken for validation, sorry, training, and similar 12 data points maybe they have taken for validation also.
Hmm.
That is the validation data. Validation data means uh, the new data set, which are the new data points which were not included in training at all.
Yes.
So on that data, when we are seeing on the 12 points, it is also still high. It is also 50, around 50, isn't it?
Yes.
So why it is so? Because of the example which I gave you. If you have a training points like this, huh,
Hmm.
like this. Now you are fitting a line over it. So your training error is
Hmm.
high. Your training
Yeah.
error is high. At the
Hmm.
same time, when you will take the validation error will also be in the same pattern somewhere.
Yes.
So
Somewhere
that
same pattern.
so that will be also high, isn't it? So that is why you see here your um, as your number of training example is around 12, both the errors are high, around 50. You just remember this value 50. Okay. So both my training and validation error are high, and that is what I have also told you previously, that in a high bias scenario, in a underfitting scenario, both your training error and a validation error are high. Okay.
Okay.
In this
Okay.
scenario where I told you here, on the training data also it is high. The training data cost function is also high, and for the validation data, this crosses basically. The cost function is also high. Okay.
Because of both are linear.
Yeah, both, because
Maybe.
both validation data set and this are coming from the same pattern, and the line which is
Hmm.
fitting is linear, just a line.
Yes.
So the difference
Yes.
between them are high. It is not able to actually fit it properly. If this could be a line
Yes.
if this could be a fitting like this will be a solid fit, isn't it? This will be a good fit.
Yes.
So on the validation data and the training data, both in both the cases, the error is around 50. And this
Okay.
plot actually has been made how? I mean, how this plot has been made? Initially, they have taken, just two training points. Then they are
Hmm.
increasing the training point, 3 training point, 4 training point, 5, 8, 9, 10, like that they are increasing. So what we have seen was on 12 data points. So on the 12 data point, this was the error, around 50. training, and
Hmm.
validation around 50. Okay. Now,
So seeing this graph,
yeah,
so I can say like if the data point is increase, the training data error is increase, but validation data error is decrease.
yes, yes, yes. The training examples, as you have increased the training example, see what is happening in this particular case is, I will tell you. Initially you had taken only two data points for training. Okay.
Hmm.
So
Hmm.
it has fitted it very well with a line. With a line
Okay.
it can fit the two data points. Na? So that is why the error was
Yeah.
almost zero.
Error almost zero. Yeah.
But now what you did, you increase the training example. So the training example, as you increase, it was like this. Now when you do
Yes.
this, it is not able to fit it. So the
Of course.
little bit of training error increased. Now when you did
Hmm.
six, when you took six training example, six like this, this
Hmm.
was the kind of data, right? Which we have seen.
Yes. So yes.
This was the data. So as you increase the training example, now your line fitting, whatever you did, has even more error. The accumulated error has gone up. So that's why it has
Increase. Yeah.
increased more. So with 12 data point, it has come to this 50. Okay. So basically, if you have only
Okay.
2 point, you can fit a line. If you have a 3 points, still you will be fine. But as if it is a curvy in nature, if the data points are curvy in nature, you will find a problem when you have more number of data points. So that is why with 12 it has more training. I mean error. And with the validation error, what happens? See, when you have only two data points, you fitted a line. But the validation error was on this particular curve, isn't it? On this particular curve. So,
Yes.
I mean, your training data point actually was something like this, right?
Hmm.
So your validation error will be somewhere here or here or here. So that's why there also the error was more. That is why
Okay.
validation error, if you will see, it is started
Increase.
from
Yeah.
a high value. And then
Hmm.
as the validation data also you increase, it came down to same, almost
Decrease.
same
Yeah.
error. But the point is, both the validation and training error are high. Now
Okay.
in the
Yeah.
next step, what we are going to do is we will take a higher degree model. We will take a higher degree model, and then we
Okay.
will see how it is fitting the line, how it is fitting the data points. Okay.
Okay.
So,
Okay.
so I will close this also. Okay, then the new picture will come. See, this is a polynomial regression degree 2. Now you see, till now we have, or what we have seen is we have only fitted a line, right? Now on the same training example, 12 training example, this was a 12 training example, right?
Yeah.
On the same training example, earlier I was fitting a line like this,
Hmm.
isn't it? On the same training
Yes.
example, I have fitted a curve of degree 2. See, just one curve there. There is only one curve with a small bend.
Okay.
So this is polynomial regression because it has degree 2. Degree 2 means if you will see the equation, it will be something like this: theta naught plus theta 1 x1 plus theta 2 x2. Sorry, theta naught plus theta 1 x1 plus theta 2 x1 square, degree 2.
Yes.
So this
Okay.
is a line which is, now if this line you will fit, whatever be your application, it will perform very good, isn't it? I
Hmm.
mean, if
Yes.
suppose the cells of the flat, the data points are like this, and you are fitting like this, then on the validation error, the error will go down because this is a very good
Yes.
fit, isn't it? On the training data,
Yes.
at least it is able to fit everything well. Don't you think so?
Yes.
So,
Yes. Yes.
so suppose your validation error will be here or here or here, your validation data basically maybe here, here in the same pattern. So it will also fit very well, right? So now if you will see the curve, you see the curve. Can you see the training curve? This blue one?
Okay. Blue.
It's
Okay.
very less. Do you remember the value of training error when we were fitting a line?
Hmm.
Do you remember?
Yes. As a degree increase.
It was
As a degree increase.
no, that is fine. I'm telling when we were seeing the same training error and validation error diagram for degree 1. That
Okay.
time, if you remember, what was the training error and validation error? I, I, I told you that you remember this value that was 50.
Yeah. 50.
The
Yes.
error was around 50. Now you see
Hmm.
how the training error is almost zero.
Oh yes.
You see, it's
Yes. Yes.
almost zero. At 12, it is something maybe one or two error is there. And validation error you
Okay.
also see on 12 or say 12 data points, you see it has minimized to maybe 10.
Yes.
So
Decrease.
validation error and training error both has gone down when we have used degree 2. Okay.
Okay.
So this is what degree 2 will give you. Okay. Now let's say so degree 1 we have seen a high bias scenario where the
Hmm.
training error and validation error both were a high around 50.
Hmm.
Now in this
Yes.
particular scenario when degree 2 we have used, we see that um the how the training and validation error both have gone down. Okay.
Okay.
So yeah. Now if so in this program also what I have done just to show you how a degree 8 curve will look like. Maybe I have coded for degree 8 or degree 6 that I have to maybe look for. But I think I have coded for yeah. So in the same example which we have seen, see on this training data point when we were fitting a line, we had 50 error, right? We have around 50 error where my training error was increasing, and with 12 data point it has reached to 50 and validation set also has reached 50. Okay, that's one case. Now in the second case, we have taken a polynomial regression of degree 2, okay, where uh, this line is fitting my training 12 points, and of course uh, on the validation set also it will perform very good like this, right? So what is happening, the training error is also very less and the validation data set also has a very less error, although there is a difference between validation and training. So because validation data will be on the same pattern, unseen data it is, na? So it will be little bit in not exactly fitting the training trend, but yeah, it will be nearby it, so the error is little bit high. Okay, so this is the program which we have done here in two phases. Basically, in one phase, I am doing regression on a line. Then in the second phase, I am doing regression on degree 2 polynomial. Now, just to show you how a degree 3 will look like, I will change the degrees to 2 and 3. Sorry, 3, and then again rerun the program. So the first part of the program of fitting a line will be same. Now see how a degree 3 line has come up. Can you see this? It is it
Hmm.
has the more curve. I mean
So it is degree
yeah.
degree 2 or degree 3? Is degree
It is
2
degree 3.
mentioned?
It is degree 3.
Right.
Okay,
Okay.
actually this label I had to change. I will show you. Actually two three places you have to change. See this is degree 3.
Hmm.
The title
Okay.
here
Okay.
degree 3, because see I am using degree 3 and degree 3 here, right? So now if you will
Got it.
see, so this is how degree 3 looks like, a more
Yes.
curvy. Okay, now if I will show you, see the error also if you see is kind of same. The validation error has on the 12 data point, the validation error is something around 10 or whatever, and this is the training error. Okay, Now if I do, and if I go for degree 4, it will be little more curvy, degree 4, and maybe in the title also I will change so that there is no confusion, degree 4. So let's say how is degree 4 behaving? See, degree 4 has like even more curve, right? Even it has two curve, right? And it is now fitting the training data even more well, right? I mean, passing through this data point, it couldn't pass through because of the degree 4 nature, and whatever it could have passed, it has passed, right? And if you see the training, now see the training data, training error. You see the training error, it is almost zero. With the 12 points, it is zero only, isn't it?
Yes.
It is totally zero. If you remember degree 2, it was some error was there, maybe one or two, but something was there. Now it is almost zero. And validation error, if you will see with 12, it is same 10, 10 or 11, it is
Yes.
same. Right. In between with 4 number of data points or with 5 number, it is fluctuating. Sometimes it is decreasing, sometimes it is increasing. But yeah, finally with 12 data point, it is around this one. Now let's say go for degree 5. Degree 5 will have even more curve, right? Like you,
Yes.
what you will be seeing in the nature is it is going more curvy and like that, right? See, I will show you. The first part of program is same. See, it has even more curve. I mean, it has actually tried for curve, but though the data points are not like that. See, here is one curve, then here it has tried to go ahead, and then, but again, because of the data points, it has come down. So then again here a curve. So this is a degree 5. If you will go for degree 6 again, but you know, as the data pattern itself has a degree 1 or degree 2 or degree 3 kind of pattern is there, so you will find a lot of curviness in maybe at the starting or the end, but this part will be smooth only. If you see the error, see the training error is almost zero, because training error it has overfit. Testing, the validation error, it is again the same around 10 or something, although it is a little bit fluctuating because of the high degree. But yeah, if you let's say we take degree a huge number, say 20. I don't know how it will look like on, or let's say 10. 10, not, we will not go that huge, but let's say 10. So you can basically, what I mean to say, you can play around, although the data points are very less. See, when you will actually get some problem, you will get at least 100, 200 data points, isn't it? But in
Yes.
this
Yes.
case, whatever open source data was there, which I have tried, the number of data points are less. So that's why it is not truly showing that nature. But yeah, now if you see, yeah, so this is degree 1. See, degree 10, it has gone something like this. So initially, actually, the graph has changed. Why this graph is
Hmm.
changed? Earlier it was starting here, it was somewhere around 0. Now it has gone, it has taken a huge dip. So it has gone towards minus 60. But you don't worry about that. You can think of like this data point has started from 0 only, like this. Okay. So basically the data points are varying between 0 to maybe 40.
Hmm.
That's always the case actually. If I will go down again, na, see, maybe with degree 3, I will show you again. Where was another degree? Yeah. The data point on the y-axis lies between, see, see. This data point lies between 0 and maybe 40 or 50, right? This 40 or 50. But when I am doing degree 10, this minus 10 shoots to minus 400 or 500. That's why the this data point seems to be on a straight line, but it is actually varying from between 0 to maybe 35 on y-axis,
Yes. Yes.
isn't it?
Yes.
So that's how you can fit a polynomial curve also. And okay, now I will just show you. So this was the part which I just wanted to show you in order to see how you can fit a polynomial curve, and you can validate your, through validation data you can validate your error also, that how it is decreasing or increasing. So
Which is the ideal one?
yeah, so the basically the first degree was not totally ideal, because that was the training data itself was high as 50, but degree 2
Hmm.
seems fine. So with degree, so unnecessarily why to go with higher degree? I mean, in machine learning there is a saying, there is a basically, what do you say, fun, somebody said something which is followed, and that is the principle of machine learning, you can say. So there is something called as Occam razors principle. Okay, so that principle says, and this is just out of stuff I am telling you, uh, uh, that Occam's razor principle says that make your model as simple as possible. A very simple
Okay.
line, no nothing technical, nothing. So but he was a big shot in machine learning field. So he used to say that. Uh, he used to say that you make your model as simple as possible. So then with degree 2 you are getting that validation error around 10. With degree 3, 4, 5, with everyone you are getting the same validation error around 10. So don't go with higher degrees, because higher degree will have more variance. So just degree 2 you can take in this example. Like just by seeing the data point I can say degree 2 will work fine, because it has just a single curve, right? See,
Yes.
the data point was something like this, right? So just with one curve it can fit well. Maybe degree 2 or maybe degree 3 will work very well. Okay. So if you will get the data, the training point or something, when you get the training data or some data from client, you will first divide the training data into 60% of training. This is a general and a golden rule I am telling you. Everyone follows this only. 20% of data for validation and 20% of the for test. So on
Okay.
60% of data you train your model, or 20% of the data, validation data, is used to choose the degree. This is a specific to regression problem I am telling you. On 20% of the data you choose the degree, which degree suits me best. So what I am telling you, with a higher degree, you will find that your validation error is increasing again. And then, and say, suppose in the same example, when I was taking it, how much I had to? 10, right? 10 or 20.
10. 10.
Okay. So when I have taken 10, on 10 it has done something like this. And when then you see the validation error, the validation error in between, it is fluctuating very hugely, right? The error, you see, what is the error here? What is the error here?
Yes.
1 lakh.
Lakhs.
So with the validation error is, even if you take a small thing like this, this will be even in thousands. This is 1 lakh. So when you with a higher degree, you will find your validation error is huge, and with a lower degree, you will find that your validation error is 50. Like with degree 1, you will find that your validation. See, what was the essence of this program? With degree 1, your validation error was 50. With degree 2 or degree 3 or degree 4, your validation error was around 10 or 12 maybe.
Mhm.
With a high number of degrees, your validation error was more fluctuating kind of thing. So don't use these degrees. So maybe you will choose degree 2 or degree 3. Okay. So this degree
Okay.
choosing is done through validation error, and on the test 20% you will now test your accuracy, and you will tell the client that this is the accuracy I am getting. You will not quote the accuracy of on 20% of validation. No, no, no. You don't have to do it.
Hmm.
You cannot go to client and say that I am getting only 10% error.
Hmm.
Because on that 10-20% validation data, you have tuned your model. So again, basically, you have fitted your model according to the 20% validation data. No? So that data, that is not a generalized error, that is a validation error. This error is called as training error, this error is called as validation error, and this error is called as test error. So basically,
Test.
what accuracy you claim to the world is the test error. See, why don't you claim your accuracy on training error? It will always come 100%. With higher
Hmm.
degrees, with a degree 4 or degree 5, your training error will be always 100%. So why don't you go and just claim that I am getting 100% accuracy? Because when you get that model to the real world and on the unseen data when you will perform, then it will perform very badly. Because it has fitted the training data so well, that is why the training error was 0. But on the unseen data, it will perform very badly. Similarly, similar to the concept, you also do not claim your error on the validation error, because on the validation set you have chosen your degree, so you have basically tuned your degree depending upon the validation 20% data, that I am degree choosing degree 2 because degree 2 performs very well on 20% of the validation data. So you have
Okay.
included that validation data while choosing the degree, right? So even on the validation set, you cannot claim your accuracy. You will claim your accuracy on test set, 20%. Okay? Because test set was neither involved in training nor involved while choosing the degree. Good enough?
Okay. Okay.
So
This is the
that
ideal
is
figure.
a what?
60-20-20 is the
Yes,
ideal
yes,
figure.
it's the ideal figure. It's the ideal figure. Everyone uses this. I mean, even you see the videos of the big shots like Andrew Ng or someone, they will also. Uh, I mean, see, a lot of people have a bad practice of just using the validation set and claiming accuracy on that. I mean, they will consider they will do 80-20. 80% training,
Hmm.
20% testing they will do. This is a general scenario actually. So everyone follows this. But a good practice is to divide it in 60-20-20 and then claim your accuracy on the final 20, the test 20. So the good practice is this. Uh, Even if you will see the this machine learning people, they will be recommending you to divide in 60-20-20. The problem is when you have huge data, say you had 20,000 data point, 20,000 observation, then there is no problem. You can split it in 80-20. Because when your data set is very high, even the 20% of the 10,000 data will give you 2,000, isn't it?
Yes.
So on the 2000 data point, if you are getting say for degree 2, you are getting very less error. So that is generalized, right? You can say that 2000 data is a good enough number to generalize my error. Okay. So in those cases, 80-20 rule works fine. But when you have very less data, say just 100 data points, then on just on the validation data, you can, if you are claiming your accuracy, it's fine, you can claim, but it is not recommended because maybe that degree has been tuned on your validation set. Maybe on the test set on the new unseen data on the client side, it may perform bad. So it's better to claim your accuracy on totally different data set, which is neither involved in training nor involved in validation. Good enough?
Yes.
Yeah. So that's the whole funda of regression, and I mean this basically completes your linear regression model. So now you can say that you have completed your first machine learning model. So yeah. So
Uh, how this useful for machine automation? This regression model.
machine automation, I will tell you how it is useful. In lot of problem, you would like to see, I mean, you would like to maybe predict things. Okay. Now these predictions till now were done manually. Okay. Example, I told you about this particular thing. What do you say? This amount of heat generated in the server room. Okay. Amount of
Mhm.
heat generated in your server because of the workload, or because of the fan speed, or because of the number of programs you use running on the cluster on the server, or because of the number of users online. Huh. Now this thing, people have to, manually monitor every time that okay, this thing is increasing, the load is increasing, the heat is increasing or decreasing, like that, right? So what you can do, if you can put a linear regression software in place which can predict that how much heat will increase with this kind of workload. So before any damage is done, or anything, a fire breaks out, or before anything happens, once the workload or those criterias goes up, your linear regression model predicts that now the amount of heat which will be generated, it is predicting the value of amount of heat which is being generated, that is going to be high, so it can alarm beforehand. So you don't have to monitor anything. You just, when you just listen to the alarm, then you just go and maybe switch off the things, or maybe you can put some users offline, and maybe whatever measures you have to take, you can take. So automation, machine learning is hugely used in automations. Okay, I mean, any model you take, you can automate lot of things which you are doing earlier, which you were doing manually. Now you are doing it through software. Like I will tell you this now, this is just the heat, this heat server problem which I am telling you, the heat server problem. This is one of the
Mhm.
problem, but actually I'm telling you, in banks I have heard this. I don't know whether what is actual thing, but I have heard that in some of the banks, to give a particular person loan, that you know that whether the person will pay back the loan or not. I mean, the whether the person, or depending upon the different criteria, like what is his salary, what is, how much income tax he is paying. Okay, those things, it can predict that whether they are going to pay back the loan amount or not, or how much amount they are going to pay back, how much loan we can sanction. So those amounts can also be predicted through prediction. Although, see, I know this for sure that decision trees are used for this purpose, but yeah, regression can also be used. Then housing price cost, I mean, this house price prediction, lot of things are there. So I was training a 10 years, uh, 10-year experience guy who is in Accenture in Bangalore. So
Okay.
he showed me an example uh, from his software. So it was basically a tool which was using linear regression. So there were almost 10 to 12 properties, 10 to 12 features for their particular company or for their particular application. On that, they were doing linear regression and predicting some values. So like that, there are a lot of application cases. Mostly, I will tell you, linear regression will be used where you have to predict some real values. Okay?
Okay, so once we train the machine,
Yeah.
it predicts automatically what the
Yeah. What is
future value.
going to, yeah, whatever is your Y, whatever thing you want to predict, it can predict that what will be the value of this. Okay. Like that. So if it is your software is basically reading the number of online users, the number of programs running, the workload of CPU, these criteria it is say every 10 second it is reading this criteria. So every 10 second it will read, and then it will predict the amount of heat generated. Then every 10 second it is doing automatically, and it is predicting every time the amount of heat generated. If the amount of heat generated say crosses the threshold, you can put the alarms, and then the whatever measures you can take. I mean, you can go and take those measures in order to prevent some damage or something, some fire break or somehow. So those kind of things
Yes.
can be prevented automatically through alarms, which linear regression and of course predict.
Yes. Yes. Yes.
Okay,
Yes.
yeah. So if you see this program, this here I am loading my data. This is a mat file which consists of the x's and the y's. Okay. So
Okay.
from
Okay.
this data, if you see, I am taking the y train and the x train. Okay, I'm loading my training data. See, you don't think much about, like in the linear regression we have seen we have a text file, right? Comma separated file. From there,
Yeah.
we
Yeah.
have taken first column, second column. I mean, in real time, real life, you will never get a mat file for sure. So this is just a MATLAB file which I have taken from some course, online course which they teach. I mean, the Andrew NG teaches that. So from there, I have, just for example, I have taken this MATLAB file. In MATLAB file, you have you save it like this is your x and this is your y. So this data has been loaded, and the y y is basically here what, the amount of water which will flow out. Okay, so
Okay.
that, and x is what, the change in water level. So these two
Yeah.
things you have taken. Now in the same data you have a validation set also. So validation y and validation x also you have taken. Okay. So this is how you
Okay.
read your data. Then this is just plotting. Okay. This is like you plot those all the training data points. See the training data point x and y, right? This is how we used to scatter, if you remember, right? This is nothing but just the red colors will be there, the marker will be x, right? If you see, if you run this program, you will see this red color x markers are there, na? So this is because of this
Mm.
red and marker x. Line width will be 1 or something like that. So those things they are showing. Okay. Now here I have trained my
What is
linear regression model. Huh.
what
And
is that one like function? NP1 underscore like.
okay. So this actually, in this x and y, whatever the amount of the change in the water level, and the change in the water level is x, and y is basically the amount of water which will flow out of the dam. So in this function, see, how do you write your formula for, how do you write your hypothesis? Theta naught plus theta 1 into x, isn't it? So this x you know, right, from here, data x,
Mm.
and data y. So data y is the amount of water which will flow out, and this is the change in the water level. Now this np dot 1 slide will basically append 1. It will append 1 to each of the data point. Why? Here it is x and here it is 1. Nothing is there, so basically 1 is there, right? Theta naught into 1 plus theta 1 into x. This we can do, right?
Yeah.
So this basically, to append this 1, they have done it. So every x, whatever, say x is 20, 30, 40, like this, change in the water level, they have appended 1 to them. Even if you do not append this one, it will do. This is basically the MATLAB funda, so they have done it. Okay.
Okay.
So this
Okay.
is basically, it is appending 1 to this file, nothing else. Okay. And after this, after plotting, you are doing nothing, just you are taking the linear regression model and you are fitting through the X train and Y train, your training data, just your 12 points, right? And then
Okay.
you are predicting your training model, that you are predicting, right? Your training data you are predicting through your model, and when you predict this, what it gives you? It gives you the line. If you remember, if I do it a scatter, you remember we have seen that the
Yes. Yes.
predicted values will give you a line like this.
Mm.
If you plot it, then it will join those points and it will give you the line.
Yeah.
See this line. How is this line made? This is like the predicted. This is the predicted thing, right?
Yes.
Anyway, so that's the thing, and then you are showing. So once you do this show, the first model, the first figure comes out. Okay.
Okay.
Yeah. Now, in this particular example, in this particular portion of the code, what I am doing, this graph actually which you see here, na, this one. This one is plotted through
Mm.
this particular code, where in loop I am increasing the number of training example. And every time I am increasing the training example, I am keeping the values of training and validation. I am marking down the values of training error and validation error. Okay. So that's how you see you have n number of samples. You see from X train, I have taken how many rows? So we have 12 data points, right? So
Okay.
validation error and train error, I have made an array with np.zeros. I have made a 12 points. It is a 12 points array. It is an array with 12 length, right? Now on this array of 12 points, you see I am looping through 12, I ranging from 0 to maybe 11, and every time I am creating my x and y with increased number of samples. So initially it will be just one point in x and y, then 2, then 3, then 4, then 5, like that till 12 I am going. And every time I am again taking the linear regression model, fitting it, predicting it, and calculating the error, train error and validation error. So once I am predicting the training error, which is x, and another time I am predicting the validation error, which is spread well. And with the training error, with the training label that is spread, whatever it predicts on the training error, say training data, on the training data, whatever my line predicts, that values from that predicted value and the actual value, I have calculated the mean squared error. This is the train error. And then from the same model, I am predicting the validation data. So that is this spread well. And I am calculating the mean squared error between the predicted value and actual value for the validation set. That is my val error. So this in loop I am doing it for 12 times. And when you plot these 12 time, in loop, you will get this. You will get this.
Okay.
So for one time it was there, then here, then here, then here, then here, then here, then here, maybe like that it is moving for validation error and the train error. So I am checking both train error and validation error. How are these different? Train error is basically the mean squared error on the training data. So whatever you have predicted through training data, that you will calculate. That will be a predicted value and this will be your actual value. Now when you do it on Excel, that is your validation set, then it is basically the validation data, validation prediction. So the predicted validation data and the actual validation data, actual validation.
Okay.
So on that you have calculated the error, which is validation error. Now what you do, you simply plot them. You plot this train error and validation error. This is your train error. 12 times it has kept values, and this is the validation error.
Mm.
So that you validate whatever x, y, label, legend, all those things you can do. I mean plotting. I mean plotting. You can search on net. See, whenever you are thinking about plotting, I mean, what I usually do, because there are a lot of things in plotting. Now every time you cannot go and read everything on plotting in Matplotlib. So usually whenever I have to plot something, I will just search on Google and I will get the codes maybe for plotting whatever 3D, 2D, whatever plot you have to do, and you can just write. So these are just the ways, plt.title, you can put title, X label, Y label, legend. Legend, no? This is legend, called legend.
Yeah.
This one, this thing is called legend.
This is yes.
Okay. This is called as X label. This is
X
called as
label.
Y label, error. And this is your title, linear curve for linear regression, learning curve for linear regression. Okay. So now this whole thing I have done for degree 1.
Degree 1.
From here, from reading the values from here, I have done for degree 1. Now I am doing it for degree 10. Same linear regression, same fitting. And again same, now here again plotting the thing, see, scattering the data. Okay. And then plotting the lines for this degree 10 polynomial. I will come to the feature part, but yeah, the learning part is same, plotting it. And then again the same looping kind of thing. Again I have taken train error, val error for the polynomial data, like 10 degree I have taken. Again in loop I am taking, like initially 1 1 value, then 2 2 3 3 4 4 in the x and y both. So I will go till 12, but I am fitting a 10 degree polynomial. So I have to first calculate the features, then same regression, fitting, prediction on the X train training data, and calculating the error on train data, then prediction on this I will come to, then prediction on the validation data, getting the validation y, and then again validation error poly, that is the mean square between the predicted value on the validation set and the actual value on the validation set. What extra step you have to do here is, just see, when you are fitting a degree 1, what is your equation? Theta naught plus theta 1 x, isn't it? X1,
Yes.
right? Now when you are plotting a degree 10, you have to, what will be your equation? Theta naught plus theta 1 x1
Theta 1
plus degree 10,
plus
what will be your equation? Theta 1 x1 square
X
theta 1 x1 cube dot plus
10.
theta 9 or 10 x1 degree 10. This will be your value. So basically from your x1, which was actually amount of change in the water level, from x1 calculate x you have to calculate x1 square, x1 cube, x1 4, x1 5. These things you have to derive, na? These things you have to calculate, all these polynomial features, right? So that you can fit it in this equation, isn't it?
Yes, yes.
So basically, if you see here, this part was clear, right? This part was
Yes.
just the degree 1 part, right? See here, from
Mhm.
when I took degree 10, this poly equal to polynomial feature degree equal to 10. Here it will go, right? So this polynomial
Yeah.
features is basically a function in here. In sklearn.preprocessing, there is a function called as polynomial feature. What it does is, when you give this polynomial feature, see, when you see here, I have just created the polynomial feature model, that class, that constructor call I have just done. I have initialized the poly object, right? With this, that
Okay.
our degree is going to be 10, you have just started the object. You have initialized the object. Now with this object, when you give it the x-train, when you are giving x-train, it means you are giving x1, isn't it?
Mhm.
If you see the graph, this is your x1, right? And this is your y.
Yeah.
So you are
Yes,
giving
yes.
x1 to this. So when you give x1 to this and you do that poly.fit transform, because it knows the degree, in this x-train poly, what it will do, it will calculate all these x2, x1 cube, x1 4, x1 5, x1 10, till everything it will calculate,
Okay.
and this has become now your new feature vector. On this you will do the fitting. See, x-train poly.
Okay.
Because you cannot just give it one value, no? Otherwise it will be again degree 1. For degree 10 you have to first create the features, all the 10 x1, x1 square, x1 cube, x1 4, all those things you have to create, and then you have to pass it to the regression model. Okay?
Okay. Okay. Okay.
Okay. So then again, this is the plotting part, scattering, and the same thing has been done here again when I am doing for 12 number of times in iteration in order to plot the fourth diagram. Again you see, I have taken degree 10, again I am first creating the polynomial features with this in the loop, and then I am passing this x-train poly in here, and then I am predicting through the x-train poly and on the training data, and then mean squared error. Now validation data, again validation data has to be also transformed in order to get the 10 degree polynomial, 10 degree features, right? 10 features, x1, x1 square, x1 cube, like that. So from validation data also I have transformed. Then I have predicted it through the validation data, well, and then you mean square error you can calculate and you will get the validation error. Okay?
Okay. Okay.
And finally you have plotted them. See, that's what I am telling you. This Python program, I do not expect you to maybe line by line, understand, because as you will progress in coding in Python, I mean, frankly speaking, like this plotting, maybe this plotting things or whatever, these things, this also I have seen somewhere, of course. I mean, I have seen on internet that how these things are done, and then I have incorporated these things into the program, into the learning curve, because I was doing some online course of machine learning maybe 2 3 years back. Then I have went through these examples. So I do not expect that you should know everything out of this, because maybe once you will be practicing Python, maybe 1 month, 2 months, you when you have practiced Python, then you will automatically understand these things. Okay, these things, to
Okay.
understand these things are easy. But yeah, so that's why I always encourage to start practicing Python a little bit. Okay, because in Python there are so many functions, in especially this numpy will have so many functions and they will be used somewhere or the other. So that way it is beneficial. If you get a hands-on Python, you will be able to understand a lot of codes very easily. Okay,
Okay.
so if you
Okay.
have any question or any line of code in this which you are not understanding, or at least you are not understanding the logic, you can tell. I will explain it to you again.
No, I understood.
Okay, what I will suggest you just go through this program. Maybe I will send you this program and all, so you just go through on your own. If you are not able to
Mhm.
understand, you can post a question on that classroom itself, or you can ask me again. Okay.
Sure. Sure.